Okay, so the subject of today's course is moving from the discrete parameter systems that we started with in the first course to dynamic systems of continuous time. So if we remember back to the kind of motivation problem, um, so as I presented before, if you picture we have the Earth in some kind of glide vehicle here, and say we could have a target or whatever, and then this glide vehicle comes in with some initial conditions and then flies to some terminal conditions here. The goal of this in any optimal control problem is what we're trying to find is the control history. So it's U of t. So this is continuous that reaches some terminal constraints while minimizing some scalar cost. So the thing, and then this cost could be like a negative energy, it can be time, it could be effort, a control effort, it can be anything. But the thing is that this scalar cost, this control is continuous. So it's CSU of t. So at any infinitesimally small t, we want a control. So this, So we have kind of two options. So we could either, so let me write that, controls continuous. Therefore, we must either discretize the controls or discretize the system before optimizing. And then what this refers to, that's what we call direct methods. And I may go into this more in depth at a different course or a different lesson, or we can optimize the continuous problem as a continuous problem. So this is indirect. And it might seem counterintuitive. Like the second seems more direct than the first, but the direct refers to when you implement it in a numerical computer. Direct manipulates the controls directly. Indirect, as we'll see, hopefully by the end of this lecture, indirect, the controls are specified indirectly through necessary conditions. So we can do the second one. So let me. This is what we're concerned with, right? So we can. So just as calculus, like we did in the parameter optimization lesson, can minimize functions of discrete parameters. Calculus of variations, minimizes functionals. So, yeah, functionals, which for this case you could think of as functions of functions. Dependent on continuous variables. So you could think of this as, right, here you might have some j of u, where u is discrete, and then here you might have some j of t u of d. Put that there. So in this case, we have a finite many u's, like elements of u. Here, u can change with time infinitely many times. Okay. So moving on. So as we build up this kind of calculus of variations, I'm going to make a distinction between the derivatives you know and love and variations. So in calculus, a derivative measures the change of a function when a variable changes. So simply, this is fairly simple, but we have some delta j of u, and then that equals to, this is this kind of like, this is just the Taylor series, right? The partial of u, the partial of j with respect to u, evaluated at some u star du, and then we do that. The second order change okay, and etc. Likewise, in calculus of variations, a variation is the measure of a change in a functional. So in that case, we have some, and I think I forgot to mention that these functionals are all scalars. So even though we feed in vectors, the functionals themselves are scalars. So we have j with j of y plus this change in y minus, it's actually variation of y, and we have minus j is equal to the variation of j plus, and then it looks the same as above. Okay, so this is the first order change. This is the second order. So it's like normal calculus. Okay, so yeah, it's like a squiggly delta. Okay, so to get a sense of variations, um, we picture a function y um, scaled by an additional parameter epsilon. So like I'm going to quickly draw out. So then we have some y of t epsilon. And then just for, this isn't super consistent, but y of t is equal to y of t epsilon naught. So we have t here and y here. This could be our y. Y of t epsilon 1, and then we could even have another one. So see how this epsilon just kind of scales everything? Okay. So using the kind of same expansion, Taylor series expansion as above, we can say y of t epsilon is equal to y of t epsilon naught plus partial y partial epsilon evaluated on epsilon naught, and then some epsilon minus epsilon naught plus, and then we're going to ignore higher order terms. And for convenience, I'm going to say this is delta epsilon, or d epsilon. So if d epsilon goes to 0, and this is like the kind of basis of calculus, and I'm going to label this right now. This is the variation. We care about the first order variation here. So the first order variation is equal to, I guess I should say it the other way. As d epsilon goes to 0, we're going to define the variation is the variation y is y of t in epsilon minus y of t epsilon naught, which, if this goes to 0, is equal to this up here. So then that's equal to, does that make sense? So this is kind of what we care about here. Okay. Any questions there? If not, we'll continue forward. So we're going to, first, before we get to the dynamic system, we're going to optimize the continuous system. Okay, so we want to minimize some cost functional J of T comma U, let me, T, UT, there we go, J of T and UT, with respect to UT. So this is, so we have min J is equal to, and for now we're just considering the path cost. So this L is equal to the path cost. We're going to ignore initial and terminal costs for now. And right now, T naught and Tf are fixed. So, like in parameter optimization, we, a necessary condition let me put A there, is this, instead of the derivative of J, instead of the dJ is equal to 0, we have variation of J is equal to 0. Okay. And so this is kind of a goal here. So to analyze the variation of J, we need Leibniz rule, and this is kind of an aside. We're using it right away. But for those who don't remember, because I kind of always have to look it up every time I use it, so if we have a derivative with respect to x, some integral from a of x, b of from a x to b of x of f of t x dx, dt. If a and b are finite, which I'm just going to assume is the case, this equals to, I'm just going to write it out. So basically we have the function evaluated at b times the derivative of b with respect to x minus the function evaluated at a. I guess I changed the order. No, I didn't change the order. These should be x's. And then the derivative of a with respect to x plus, and this is kind of the important term right now, the integral from a of x to b of x of the partial with respect to x of f. So the reason for doing this is that the main takeaway is this allows us to take this derivative outside of the integral and put it in as a partial within the integral. So we can move through the integral sign. Okay, so then we apply that to J. So we have we're going to take the derivative with respect to epsilon. So we have this, I'm sorry, there's no J there. L of t and u dt. Okay, so since t0 and tf are fixed, that results in this the partial of L with respect to epsilon dt. So yeah, once again, time is fixed on both boundaries. It won't be in the future, but now it is. So then we could expand this partial out, and we can have the partial of L with respect to U times the partial of U with respect to epsilon dt. Okay. And then we multiply both sides by epsilon naught, and we evaluate. How do I say this? I don't know how to say it in words, but basically we evaluate this here. So this and this, we evaluate at epsilon naught, and then multiply both sides by epsilon minus 0. So we get and then remembering how we defined a variation. So we're going to take this to 0, and then we get delta J, right? And then this is equal to TF. This is the subscript, L subscript U, so the partial of L with respect to U of the variation of U dt. And once again, we want this to equal 0. So as a result, we get, for any, this could be, this delta U can be anything. So our necessary condition is that L sub U is equal to 0. Any questions there? Okay, that's great. I need a drink, so I apologize. Okay. Okay, I'm sorry then. We have a lot to cover, so I'm sorry for really pushing through it. And if you miss anything, I will upload these written notes, and then sometime in the hopefully not too distant future, there will be typed out notes available as well. Okay, so here we're going to move on to the continuous system. So, yep. Yeah, so it's like the equivalent to, right, so it's this. It's like the same as a derivative, but it's a derivative kind of more generically defined. I hope that's correct. I mean, someone might nitpick what I'm saying, but from this point forward, it's basically, you could think of it as you would like dj in the sense, but it's like a more generic version. So we're going to solve continuous systems with algebraic equality constraints. So we're not yet to optimal control. But this actually mimics what we did in the parameter optimization. So we minimize J, and the same things that are going to apply here as before. But we have additional dependent set of variables x in addition to u, and that's subject to some constraints is equal to 0. Like I said before, t's naught and tf are equal to 0 as well. Oh, it's not equal to 0. Are fixed. So we adjoin constraints to path cost L. So in the future, we're going to be adjoining more stuff to things, and in principle, when you can really adjoin any constraints to anything in these problems. Oh, no. You can join any constraints to these problems that you wish. The rule is, though, if it's true at all times, so just something that's on the path, which these constraints up here are because we have f of t, x, and u is equal to 0, then you adjoin to the path cost. If it's something that's only on a point, then you adjoin to the cost associated with that point. And that we'll cover later. We're actually not going to do that today. But here, it's the same as the normal Lagrange multipliers. Okay. And likewise, like you would expect, we take the differential of that. So kind of skipping all the steps above. So we have the partial of L with respect to X plus this lambda. And lambda, I stopped writing all the bars over everything. So just assume things are vectors until said otherwise. So we have the partial with respect to L plus this vector of lambdas and this vector of, the constraints. Oh, and then I forgot to note something. So we have the same, but with respect to u, times the variation in u, and then we have the constraints with the variation of lambda, and that's dt, and then this is all equal to 0. Okay, I forgot to note that this lambda here is a lambda with respect to time. So this is a function too. So we adjoin the constraints of the path cost L with lambda equal to lambda of t, which varies continuously. At the optimal, based on our constraints, f is equal to 0, so this whole thing is equal to 0. So we have these two expressions. So actually, let me specify like I have in my notes. I have, unfortunately, the tendency to sometimes go off notes, and then that's when things don't go as planned. So yeah, these are equal to 0. So let me just rewrite it. And we have our original f. So here we have n equations, m equations, and n equations. So then we have our 2n plus m equations for 2n plus m unknowns. U of t, x of t, and lambda of t. So because these are, sorry, that might have it messed it up on the side, but right, these are functions of t as well. So these are true for all time. So for each period of time, we know we have an equation to solve for our unknowns. Yeah, I'll try to keep that stuff up. Okay, now we get to the fun, and I should have enough time, which is good. So if there's any questions, you can stop me. So we're going to move on to the optimization of dynamical systems. Okay, so it's similar to what we had before. We minimize J, and here I'm going to add, since we keep on adding more features, I'm going to add a terminal cost as well, T, which is dependent on time, final time, and final X, the final state vector. This I will refer to as the terminal cost, plus, like we had before, some path cost. Now what makes this different than before? Well, like before, we have T naught and TF fixed. So I forgot the 2 there. I think my brain combines 2 with T naught. So it's subject to T naught and TF being fixed, but then this is what's new. We have some X dot is equal to F. So from now on, I'm going to refer to F. It's the dynamics, or also the equations of motion. So you might guess, we want to hold this constraint. So this equation is a constraint like any other. So we just adjoin it to, put dynamics. We adjoin dynamics to the path cost. J prime. And so we're not cluttered. I'm dropping the arguments to things unless I think it's needed for clarity. So yeah, so we have this augmented path. This is equal to 0, right? Guess I should maybe make that. Start using more different colors. Okay. So then, like before, we take the variation. And set that to 0. So the first variation is for the terminal cost. So we take the partial. What changes in this? So since the terminal cost is dependent on TF and X at TF at the final time, but the final time is fixed, we only have to care about its variation with respect to the final state. And then we have everything in the integral. Let me move this down here. Actually, I forgot a step, so if you will bear with me, apologize for this. I'm going to move this down here because there's a helpful definition that I missed. So and the reason why it's defined like this you'll see later, but we define a Hamiltonian that's equal to the path cost plus lambda transpose f. This is so no, it doesn't include this minus x dot term. So when we take, so the resulting is we have j prime is equal to phi plus, then we have h plus lambda t minus, hope you're using a pencil, dot, and then, so simplify it a little bit. So going back down here, so we take the variation and set to 0. So we have a terminal, and then we have the partial with respect to the Hamiltonian of x. Variation of times the variation of x times the same thing with respect to u times the variation with u plus the partial of the Hamiltonian with respect to lambda, and then the variation of lambda, and then minus now it's this term. We have x dot transpose times the variation in lambda, so we do the product rule on this. So the product rule applies the same way it does in normal calculus, dt. So we have these terms inside. Luckily, here, the partial of the Hamiltonian with respect to lambda, if we go back up, that's just f. So this is equal to f, which then is equal to 0. So then this is equal to 0. So we can eliminate that. Okay. Now, so as of now, like we did with the parameter optimization case, we have both variations with respect to the state and with respect to the state's x, and the variations with respect to the control u. Let me. Oh, I'm sorry too. The same applies to this. So, right, x. Sorry, I missed this as well. In the same way, this is equal to f, which. Oh, I know what I messed up. F isn't equal to 0. Okay, rewind. Once again, I'm sorry. So what I wrote was right, but my elimination wasn't. So we have partial lambda variation of lambda minus x dot t x dot transposed variation in lambda as well. If we combine these together, so this together is equal to f minus x dot times the variation in lambda, which then is equal to 0. So we cancel both of these terms. Okay, now what do we have? We have variations in the states x, variations in control u, and then the variation in x dot. To eliminate this, so this x dot is the first thing we're going to focus on. So we eliminate variation in x dot via integration by parts. So if you remember, so I'm going to note because this is this aside. Integration of parts works that if you have the integral from a of x, a dependent on x to b dependent on x of some u dv dt of dt, that's equal to uv, like from a to b. So you take the integral of u and v minus the integral of a to b. I guess I don't need these x's here. It's not very important. I just put a to b. That was held over in my notes from when I was doing the Leibniz rule of du dt of times v dt. So we basically switch in the integral, we switch what's being the derivative, and that's integration by parts. So we apply that to our system. We apply that to our equation up here, which I should have numbered. Okay, so let's do the part that's sticking out. So we have the integral from t naught to tf of lambda times this, so times the variation in x dot. That is equal to applying the integration by parts. So yeah, I guess this is kind of a step that's skipped, but if you consider that u is lambda and then v is the variation in x dot, and now we get the integral. Yeah, so then this is right. So this is easy to solve because the integral cancels the derivative, and then we have this left over. Yeah, so we traded the derivative being on the variation of x for the derivative being on the on lambda. Okay, so we plug that into the variation in J prime. So we have the kind of terminal cost term And if this is evaluated, this thing is evaluated at, yeah, when it's evaluated, you end up getting, and if we go up here, see how there's a negative here, so the sign is going to switch everywhere. So we subtract this at TF. So we get lambda at TF in a product with the variation of x at TF. We do the same thing at the initial point. And then we get everything else that is in the integral. And here I'm using subscripts for the partials. Okay, so that was a lot there. And then we're just going to combine some terms. And this, of course, is equal to 0. But we combine some terms just basically here. Fortunately, going through this quicker than I thought I would. So, not as rushed for time as I expected. So we collect everything that has a variation to the final state. So we have this partial of the terminal cost in the final Lagrange multiplier. And then we have, just because we don't have an initial cost, I might make it a practice problem to solve this with an initial cost. But it's actually not that difficult. So we have a kind of initial, and then we have everything in the integral as above. So this is a little lot here, but let's break it up into terms and deal with each separately. Because the goal is to make it so that the variation in J prime is 0 for any variation in X and any variation in U. So let's take these 3 terms. So this is the first one. This is the second one. Well, let me extend this to here. And then this is the third one. So let's first start with term 2. And keep in mind that now lambda is still free. We didn't say what lambda was or what kind of shape it takes. It can be anything so far, but we're going to make it something now. So if x, so I'm indexing, so xi is the ith term of x. So if, the ith term in x at the final time is fixed, then the variation of that term is equal to 0. Does that make sense to everyone? Because I can explain it more if it doesn't. Okay, great. So we have this here, this term, the second term. If the xi is fixed, then the corresponding lambda I can be anything because it's going to be 0 regardless. But if there's some variation in x, we must guarantee that the lambda, the ith entry of lambda, is equal to 0. I'm just going to move the if down here. Is fixed, then else, if so this is what I explained. So if you have a fixed, if the ith state is fixed, then the ith entry of lambda is free, and if the ith state is free, then the ith entry of lambda is 0. And this is actually solving it in the unadjoined method. In the future, we kind of make the initial and terminal constraints more flexible, and in that case, you can adjoin them like other constraints, and you'll see that next Wednesday. Yeah, but then this holds true, and it's still good to look at this, because if you think about it, here this means we have some constraints here, so we don't need an extra constraint. So here's a constraint is on here. So regardless, we get a constraint that results. So if the state is free, then lambda is fixed, and then once again, if the state is fixed, then lambda can be free. Okay, we did the same thing to term 1. So if we look back up at term 1, it's here. It's the same thing, but instead we have this cost function, terminal cost right there. So make it so it's consistent. If is fixed, lambda is free again. Else if is free, then we get lambda I TF is equal to the partial of the terminal cost with respect to x. And that this is at, sorry, that was messy. It's x at TF. Okay, so we basically, same dynamics up, same dynamics with this as before, that you get a constraint regardless. So if the constraint is on the states, you get it there. If the constraint is not on the states, you get it with the Lagrange multiplier. And then we need to know what these multipliers do between, so during the integral, so during the dynamics. So we need some dynamics for them. So if we look back up at term 3, we want to eliminate this variation in x. So we set the what's in the brackets there with to 0. Yeah, I have it correct. So then, as a result, sorry, that should be a dot. Did I miss that when I copied? No, I have it as a dot there. Okay, so now we have dynamics. So we have, if we need them, we have additional boundary conditions for the what we're calling the Lagrange multipliers, and then we have dynamics for Lagrange multipliers. And I probably should have said this before because it would have been easier to speak. But we call lambda, we refer to that as the costates. This is because you can see here, well, you can also see from the dynamics, for every state we have a costate. So they're also in some places referred to like as dual variables. Yeah, so from now on, every state's going to have a partner costate. Yeah, so as we eliminated all the variations of x, I skipped words. Yes, I just forgot you're right. Thank you for pointing that out, Eli. So as we eliminated dependence on variations in x, we get all that's left is that partial with respect of the Hamiltonian with respect to u times the variation of u in the integral, and then that's equal to 0. So here we get as a result, we just say this is equal to 0, and then this provides what we call the optimal control law. Yeah, so from now on too, you can, so see here, if you remember back to the parameter optimization lesson, we get a similar thing with the augmented cost there. But of course we get other things, but basically from now on, what I'm meaning to say is from now on, you could in a way think of what minimizes the Hamiltonian with respect to control if these other necessary conditions, and I actually have them written out as a summary on my last page. So if these other necessary conditions are satisfied, then you can think of the Hamiltonian as your cost. Here's, we have n differential equations, n differential equations, and then m algebraic equations. So these need, so if you propagate a differential equation forward, you also need a boundary condition. So these need two n boundary conditions. So then if we look at the boundary conditions, if fixed, and else and the same for the, well, yeah, for the terminal, it's the same if the state is fixed and the costate is free, else the costate is equal to the partial with respect to that evaluated at I. So this gives us n boundary conditions, and then this gives us n. So we have everything we need. So the m algebraic equations apply for u at all places, and since they're algebraic, they apply for all times. And then the n differential equations plus one of these n boundary conditions, and then these n differential equations plus these n apply for both, solve for both the states and the costates. That, of course, is all kind of intermingled, but then the accounting works out. We have enough equations. Okay, so I guess we have 15 minutes. I don't really have much more to say. I guess I can pull up an example too. So if there's questions about anything, I'm happy to answer them now, or I can work out an example. Sure. I thought this would be longer, so so I didn't have it already written out, but I have ones on hand. So this one's actually kind of cool because this isn't like what you normally think of a dynamic system. It's so a picture that we have some nose cone. Some shape here. And you would probably think of this as some kind of distance, but to keep things consistent, let's make this time. Well, it's t. So it's an independent variable. And then we specify along this at any point. You could define some angle theta that goes along here. And actually, let me say that this well, I guess to keep it consistent with so I'm going to say this is t is equal to r. And then we have some theta, and we say u is equal to theta here. So each point Oh no, I'm sorry. So this is still t, but we define an r. So this is r. Okay. And since we have this theta, the change in r for each given time, okay, is so r dot is equal to tangent of theta. Does that make sense? So, right, so this slope at any time is the tangent of this. So I guess I'll rewrite that. So these are our dynamics, and then we can, using like hypersonic, like a Newtonian hypersonic flow, we have a drag coefficient. That's equal to this. So this is based on Newtonian flow. So we can minimize, so I guess in this case we want to minimize drag. So we minimize J is equal to D with respect to theta, because that's what we change. Okay, and then this can be simplified to, well, I should have written this out. We have this whole equation, right? Oh, and that's because I forgot to write something. Cp is equal to 2, assuming that it's all going into the flow, which it is equal to, if theta is greater than or equal to 0. So we can, this is equivalent to if we kind of, these are constants, where Q is dynamic pressure, these are constants, so this is equivalent to minimizing J is equal to 2 sine squared theta times R. Wait, hold on, let me, actually, let me look at this for 1 second. I thought this was a different problem. Sorry, we're going to do the same problem, I just have to look it up. Actually, I apologize. I'm going to just cut it here. I'll include this problem as it should be in the homework, and there'll be a solution there. Yeah, there'll be a solution there, so we won't have to talk it through. Yeah, so maybe in the last 8 minutes, that would be a good idea to go through that GitHub repository. Yes, of course you can. Okay, so this this result, and I should have been explicit about this, this is a 2-point boundary value problem, right? Because in this case, right, if so it's a 2-point boundary value problem insofar as here's on the, this is t is equal to, this is t naught, and this is t final time. So we have conditions on, so if I say that the state is fixed on the initial time, then you can have states just fixed on the initial time. If I say states are fixed on the final time, so this constraint, even before adding the co-states in, we have a 2-point boundary value problem. And I probably should have been more explicit about this too, is that applying what we did today, everything we did today, we took a continuous optimal control problem, where u, want to find u, which has infinitely many points because it's continuously varying. So you take this time of infinite dimension in space, and you cast it to a 2-point boundary value problem with finite variables. Like you have finite number of unknowns. So yeah, so it still applies. So say, let's skip over this example. I'll get too fancy. I had okay, here's a, I printed out the wrong thing. But let's just do it like this. Say minimize j is equal to some u squared dt from 0 to 1. And then we have dynamics that are okay, can't make up a problem. Sorry, this end is not great. But yeah, basically you get a 2-point boundary value problem anyway. No, this, oh, yeah, so I kind of, this is the unenjoined method, but it's the transversality condition specified in Wards. So the transversality condition, and so I'm not just for reference, I'm not following 508 really. I'm following the Bryson and Ho's book and a course given by Dr. Grant when he still taught at Purdue. So if we look back up past here, so this, what we have here, is basically the transversality condition kind of embedded. So actually, I have the Langowski's book next to me. I'll write out the transversality condition, and then so we have h t. This is as given in Langowski's optimal control book. So in this case, this we don't know yet because time is fixed. So next on Friday, we're going to derive this condition here. And then this one says so this, in Langowski's notation differs a little bit because he uses D for variations. He doesn't use a delta. So this is all kind of logic that falls out of the transversality condition, but that component is really just equal to this, right? Number 2. So you have lambda t dx at t0. If we look back down here. Oh, that's a tf. And then, so, I guess he did, Langevsky also doesn't include, so if you make a transversality condition based on what we did, you'd also get this. And then that's equal to 0. But basically, you could derive the transversality condition from what I already showed. The transversality condition honestly just confused me more when it was taught to me than just saying like, oh, if you can change this part or change this part. And then once we go to the join method, you don't need the transversality condition anyway. You're welcome. Anything else?